Students, I'm Tamil Vanan. Now I'm going to teach a problem on heat and mass transfer, especially in a forced convection. In forced convection, internal flow. In internal flow case, there is a flow inside the cylindrical pipe. Let me move to the problem. In the problem, water enters at a 50 degrees Celsius in a 1.5 centimeter diameter pipe, 3 meter long tube with a velocity of say 1 meter per second. So the diameter of tube is 1.5. Its length is around 3 mm. Here the diameter is d is equal to 1.5 centimeter and the length that may be around 3 meter. Here which can be written as 0.015 meter. Here the water enters at 50 degrees Celsius. That is the TMI, that is equal to in inlet condition 50 degrees Celsius. The velocity say 1 meter per second, which is equal to u. Then the tube wall is maintained at a constant temperature, say 90 degrees Celsius. The wall temperature, there is a tube wall temperature TW, which is equal to 90 degrees Celsius. Then you are going to find two parameters. One is the calculate the heat transfer coefficient and total amount of heat transfer. So first one is the heat transfer coefficient, then second one is the total amount of heat transfer. If the exit condition of water is say that is a 70 degrees Celsius. Okay. So from the given data, you must notice what category of the problem is. First one, the condition is forced convection. How we can consider this a forced convection? Because the velocity is given. Then second condition is internal flow. How we can say internal flow? Because the flow inside the diameter of the tube, we can consider the internal flow. Then third one, you are going to find for internal flow cases and forced convection, you have to find that is called as a bulk mean temperature. Going to find the bulk mean temperature, that is called as a TM. This data is available in the HMT data book and the page number saying around 132 something, 132 something. Internal flow, so 130 something. The problem is internal flow. The internal flow, you are going to find the bulk mean temperature Tm. That is the Tm is equal to Tmi plus Tm naught divided by 2. So substitute this category in this condition. So Tm is equal to Tmi plus Tm naught divided by 2. Here Tmi is equal to 50 degrees Celsius. Then Tm naught equal to 70 degrees Celsius. So which is equal to 50 plus 70 degrees Celsius divided by 2. Then bulk mean temperature is equal to 60 degrees Celsius. Next condition, whether you are going to find properties at mean bulk temperature. Properties STM that is available at HMT data book. In HMT data book, page number around 30 something. Here we are having a property values at a liquid state. Say at condition of say 60 degrees Celsius, the fluid is water. So fluid is water. The condition at 60 degrees Celsius, you know the property values. So for a forced convection problem, three important properties are considered. So one is kinematic viscosity, then second one is a Prandtl number, then third one is a thermal conductivity. You can note the problem in the cases here. Value in the cases. Here that is the kinematic viscosity, which is equal to 0.478 into 10 to the power of minus 6 meter square per second. Then Prandtl number, which is equal to 3.020. then thermal conductivity is equal to 0.6513. So after this is the watt per meter Kelvin. After evaluating the properties, then you find what about the Reynolds number. So fifth step is nothing but that is the Reynolds number. Reynolds number, there is R is equal to U divided by, say it is nu. So U is equal to 0.1 meter per second, then diameter is equal to 0.015 meter, everything is substitute meter, then kinetic viscosity equal to 0.478 into 10 to the power of minus 6 meter square per second. After substituting the value, you can get the Reynolds number is equal to 30,800 plus 82. So this is the Reynolds number. 30,800 plus 0.82. So which is greater than 2,300. So the flow inside the tube is, that is, turbulent. Then after finding the flow is a laminar or turbulent, we are going to find the Nusselt estimate, that is Nusselt number. Nusselt number. From Nusselt number you can take a value, that is a HMT data book. From my HMT data book, at page number 130, internal flow the condition is, so there is an incentive, the conditions are turbulent. In turbulent flow there are several conditions as there, several conditions are given. One is rough tube, that is not suitable for this case. The partial transition node is not suitable, entry length is not suitable, then entrance region there is also not suitable. For the short pipe we are not considered, but in this flow is a fully developed flow, so you can consider this Nusselt number. But before you consider this condition, you must check these values are appropriate, should appropriately suitable for this condition. So first, for the Prandtl number, for our case at a 60-degree bulk mean temperature, the Prandtl number is equal to 3.020. So which is available in 0.6 and 100. So this Prandtl number case is verified. Next one, there is a Reynolds number which is equal to 30,800. So just less than 2,500 and greater than 1.25 to 10%. So Reynolds number condition is also satisfied. Next, you are going to find L by D. So L is equal to 3 meter divided by 0.015 meter diameter, so which is equal to 200. So L by D is greater than 60. So third condition also satisfied. So this after the three conditions are satisfied, you may choose the appropriate Nusselt number. In a Nusselt number, they are having another one term that is called as N. So some constant N is given. What is the N? The N is 0.4 for heating the fluids, 0.3 for cooling the fluids. For our case, the heating is transferred because the air in a flow, the air and the water enters at a 50 degrees Celsius and leaves at say 70 degrees Celsius. So the heating can take place. So for heating, you can take N is equal to 0.4. So you can note the right value and substitute in the Nusselt number equation. So that is Nu is equal to 0.023, then Re of D with respect to 0 power 8 and Prandtl number whole power n. So this formula is taken after the satisfying these three conditions. One is the Prandtl number, the next condition is equal to Reynolds number, then third condition is equal to L by D. These three conditions are satisfied, so we take this number. Now we substitute this number in the values in the Nusselt number equation. 0.023 Reynolds number is equal to 30,800 whole power 0.8 and Prandtl number is equal to 3.020 whole power 0.4, because for heating purpose we consider it as 0.4. Then after that you may get the Nusselt number Nu is equal to 139.4. This is the Nusselt number for this case. Then you finding the Nusselt number. Next you going to find seventh one, that is called as that is a heat transfer coefficient, H. So Nu is equal to, or it is equal to Hd divided by K. So you are going to find the heat transfer coefficient. H is equal to Nu into K divided by, that is the D, Nu 139.4 into diameter K, there is a 0.6513, then divided by diameter 0.015. And after substituting the value, you may get the heat transfer coefficient H is equal to 6057 approximately 6057 watt per meter square Kelvin. In seventh parameter, heat transfer coefficient is evaluated. Next, we move to the next last condition, that is equal to heat transfer. That is the Q, heat transfer. Then from the Newton's law of cooling, you already know for the convection cases, Q is equal to H into AS into delta T. The AS represents there is nothing but the surface area. So in that case, the H into AS into delta T, we may take in a wall temperature minus, here please note that, so it is like in the pipe entered at a 50 degrees Celsius and leaves at a 70 degrees Celsius because of heating. Here the wall temperature that is maintained at a temperature, say that is a 90 degrees Celsius. So the heat is transferred from wall, that heat is taken by the fluid. So in a case of external flow, we can take delta T is equal to wall temperature minus ambient temperature. But in our case, in the flow inside the tube, this is for external flow. For internal flow, we can note the delta T is equal to wall temperature minus bulk mean temperature. So in that case, what is the bulk mean temperature? Bulk mean temperature Tm is equal to Tm Mi plus, already we discussed Tm naught divided by 2. So which is equal to 50 plus 70 by 2. So Tm is equal to 60 degrees Celsius. So here you can write that is Tw in minus, that is called as a Tm, bulk mean temperature. Okay. Here H you can already find, that is equal to 6057. Area is equal to pi into D into L. Then wall temperature is 90 degrees Celsius and bulk mean temperature is 60 degrees Celsius. So 6057 into pi into diameter 0.015 L3, difference of 90 to 30, difference is nothing but 30. 90 to 60, the difference is 30. After substituting values, you get the heat transfer, which is equal to 25688.64 watt. So it can be represented right in a kilowatt is equal to 25.68 kilowatt. So 25.68 kilowatt is transferred from the pipe, that is where the wall temperature is 90 and the entry temperature 50 and exit temperature is 70 degrees Celsius. So this is the final heat transfer. Already we find the heat transfer coefficient in the previous page, and H is equal to 6057 watt per meter square Kelvin. Okay, thank you for listening.